In this video, we're going to be solving radical equations and then checking for what are called extraneous solutions. So throughout this unit, we've focused pretty heavily on checking our answers. And there's actually a really important reason that we do that. Not to just make sure that our answers are correct, but also because when we're dealing with roots and finding solutions, there are actually solutions that we'll find that are called extraneous solutions. So when we raise a root to a power, we can sometimes get solutions that don't actually work or make our original equation true. So here you notice we have a fourth root. Because we have an even root, we have some restrictions of the values that go inside of the root. So what we need to do is we need to check our answers every time to make sure that we don't have an extraneous solution, which is essentially a solution that appears to be true, but because of the restrictions of the domain for the root, actually isn't true. So let's work on solving this radical equation together. We know that we need to start by dividing by 4. Because we have to get the radical alone. So we have the fourth root, then we have x plus 5 on the inside, and negative 2 on the right-hand side of the equation. Now we need to undo that root, and we do that by taking everything to the power of 4. So we get x plus 5 left on the left here, and then negative 2 times itself 4 times, so negative 2 times negative 2 is 4, times negative 2 is negative 8, times negative 2 is 16. So we subtract 5 from each side, and we end up with x is equal to 11. And this appears to be our solution. Now, believe it or not, this is actually an extraneous solution, and I'm going to show you what's actually happening and why it's extraneous, or essentially why it's a solution that appears to be true, but doesn't actually make the original equation true. So if we substitute this back in, we get 4 times the fourth root of 11 plus 5, remember we're substituting 11 in for x, and we're checking to see if that's equal to negative 8. Well, inside of this root here, we end up with the fourth root of 11 plus 5, which is really the fourth root of 16. The fourth root of 16 is 2. And if you look carefully here, what's happening is we end up with 8 is equal to negative 8, and this is actually a false statement. The reason this is happening is because if you look really carefully at this step right here, you can see that we have an even root equal to a negative number. When that happens, when we have an even root equal to a negative number, that actually isn't a solution of a real number that's going to make our equation true. And so because we're taking this to the fourth power, we're accidentally creating an extraneous solution. So as we're working with roots, it's going to be really important, especially when you're dealing with an even root, that you always check your solution and you make sure that it's not extraneous. So in this case, x equals 11 is an extraneous solution because while we solved the equation and got that as the answer, it actually doesn't make the equation true. So we're going to be focusing on how we can test for those and how we can look out for these types of solutions. So let's focus on a second example together, and we'll check for extraneous solutions at the end. So if I look at this example here, I notice that my radical is already by itself, which is great. I don't have to rewrite my equation in order to take care of that first step. Now, I notice this is a square root, so what I'm going to do is I'm going to square both sides of the equation. Now, when I look at this, I notice that this is actually a little more complicated than the examples I've seen in the past. So I see here that I have x plus 1 quantity squared, which I know is represented by x plus 1 times x plus 1. So I know I take x times x, which is x squared, x times 1, which is 1x, 1 times x, which is 1x, and 1 times 1, which is 1. So after I've squared the left-hand side of this equation, I end up with x squared plus 2x plus 1. Be careful when you're squaring binomials because you're going to end up with a little bit more than you thought. Now on the right-hand side, when we square that, it just undoes the square root, so we're left with 7x plus 15. Now when I look at this problem, what I notice is it looks a little bit different than the ones I saw before. The ones I saw before were all linear and only contained x's. This one contains x's and x squareds, so I know I'm going to have to solve it in a little bit of a different way. Because it's got an x squared, I know that it is a quadratic problem, so I need to solve it like quadratics, which means I'm going to use factoring or I'm going to use the quadratic formula. So I need to start by getting everything together on one side of the equation. So I start by subtracting 7x from each side and then subtracting 15 from each side. So I end up with x squared minus 5x minus 14 is equal to 0. So I have a quadratic, and remember, you have two different strategy options for solving a quadratic. One is to use factoring, and two is to use the quadratic formula. Now, it doesn't matter to me which one you use, but they will both work. So for this case, I'm going to choose to use factoring because I can actually factor this pretty quickly by using my factoring trinomial strategy using the ABC method. So I'm going to factor this. So I have x squared minus 5x minus 14 is equal to 0. I notice that a is equal to 1, b is equal to negative 5, and c is equal to negative 14. So I'm looking for two numbers that multiply to a times c, which is negative 14, and add to b, which is negative 5. Two numbers that multiply to negative 14 but add to negative 5 leave me with negative 7 and 2. Now, because my a value was 1, I can use the shortcut that we've discussed. So I can rewrite this straight into factored form, which is just going to be x minus 7 times x plus 2 is equal to 0. Now, if we use the zero product property here, we have x minus 7 could equal 0, or x plus 2 could equal 0. You add the 7 to each side, or subtract the 2, and you end up with x is equal to 7 and x is equal to negative 2. So we end up with two possible x values that could make this equation true. Now, if you use the quadratic formula, which is definitely an option, you're going to end up with the exact same values. So if you can't remember the quadratic formula, I will write that down here for you very quickly. The quadratic formula, if you need to remember it, is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. But remember, you can use factoring or the quadratic formula. Either one will work. Now, the last step here is we need to check for if we have any extraneous solutions. Remember, even though we got two solutions, it doesn't guarantee that they're both going to work. So we're going to actually start with the x equals 7, and we're going to check it and make sure that it works. So we're going to substitute it back into this original equation here. So I have 7 plus 1 is equal to the square root of 7 times 7 plus 15. Well, 7 plus 1 on the left-hand side is just 8. 7 times 7 is 49. 49 plus 15 is 64. So I end up with 8 equals the square root of 64, which is 8. So I find out that 7 is a good answer. It is not extraneous. Now let's check x is equal to negative 2. So here I have negative 2 plus 1 on the left, and the square root of 7 times negative 2 plus 15. So negative 2 plus 1 is negative 1. Square root of, we have 7 times negative 2, which is negative 14. So I have negative 1 equals the square root of 1, which becomes negative 1 is equal to 1. And this is not true. So what this is ultimately telling me is that I have one solution that is true and works, and one solution that is extraneous. So here, what we'd write as our final answer, I'm going to move this up just a smidge. What we would write here is we would write x is equal to 7, and then you could write x equals negative 2 is extraneous. So that's telling me that you found another solution, but you tested it and you discovered that because of the limitations of a square root and it being an even root, that it didn't actually work inside of our original equation.